Hi, I'm Dave Bering, Technical Director here at TriStar, and welcome to another Tech Talk. Today we're going to be talking about something a little bit different in that we're going to be talking about designing PTFE seals. I was kind of raised in with an influence that if you have a bearing application, more than likely you're going to have a seal application too, and vice versa. So it just has come by natural occurrence that TriStar has been more and more involved lately in the design and production of seals. So we thought it'd be a good idea to talk a little bit about the different types of seals and maybe a little history of seals and where we are now today. Let's first take a look at the definition of a seal, and this is going to be the Mr. Science definition. A sealing device can be defined as a component used between two surfaces, static or dynamic, to maintain a pressure drop from a positive fluid pressure area to a relatively lower fluid pressure area for a specified period of time. That is the Mr. Science definition. My definition as a layman is a seal prevents leakage. That's it, bottom line. And it's the effectiveness of that seal and through its design and through the material that makes it a good pressure reducer or a bad pressure reducer. So we're going to talk a little bit about what makes a good seal. First of all, seals are classified as static or dynamic. If you have seen a leaky seal on your faucet at home, that seal in there, that little rubber O-ring, is typically static condition because as the valve is closed, it's in a compressed condition and it's just sitting there statically. When you turn the valve on, now you've introduced some dynamics. So there's, by classic definition, there's a static seal, which is maintaining a pressure drop between two stationary faces, and then a dynamic seal, which is maintaining a pressure drop between two moving surfaces. Now, static seals can also be classified according to the plane in which they're being used. Face seals prevent leakage in a plane at right angles to the seal center line, and they can be designed to function as both an internal or external face seal. Internal being a seal face that is producing a block of pressure from the inside of that seal, and then conversely, in an OD pressure situation, it would be an OD face seal. Dynamic seals are considered to be radial seals or seals that prevent leakage in a parallel plane to the center line of the seal. Dynamic seals are typically going to be either rod or shaft seals or a piston seal. And those seals can be further classified as rotary, oscillating, or linear. You can have rotary rod seals, which is usually referred to as a shaft seal. You can, in some cases, have a rotary piston seal. More often it's a reciprocating seal. And then there are some situations where you can have oscillation as well. Looking back at seal technology, where it's come from, if you go way back to the earliest forms of seals, back literally before the Industrial Revolution, the seals were very simple in design. A lot of these were just ropes. They got pretty smart along the way, and they would either coat them in wax from candles. In some cases, they would coat them in animal lard, basically to just give them a certain amount of lubricity and also something to keep that rope from drying out over time. Some of the seal materials that were used early on were hemp, cotton, leather, wool, and believe it or not, some of these materials are still used. It wasn't too many years ago I sold some leather piston cups to the Nuclear Regulatory Agency for use in containment at a nuclear power plant. So some things just never go away. Hemp is used for a lot of things, and it certainly could be used as a packing even today. With the advent of vulcanization came a whole new family of products. Rubber seals came along, both for gaskets and eventually in the early 30s we saw the advent of rubber O-rings. Early on, the rubber seals were sometimes reinforced with cloth or cotton just to give it a little bit of reinforcement. And some of those early designs were chevron packings. And even today, pump packings, many pump packings are still chevron packings made out of rubber and cotton cloth. So even to this day, with technology being what it is, there are some things that just still work best, even though they're the simplest design. Now, the rubber O-rings came along in the 30s. That's where you can trace the original patent to. And it was really World War II and the advent of hydraulic and pneumatic controls on aircraft that really brought that industry along. Rubber O-rings are normally seen in everything from hydraulic actuators to brake calipers and all kinds of gaskets. Anywhere that a leak could occur, there was generally going to be either a rubber gasket or a rubber O-ring. The early materials were fairly limited. It was back before a lot of synthetic elastomers had been developed, so natural rubber was most commonly used, and then along the way came Buna-N, which we know is nitrile, and then the synthetic materials came along rapidly after that. Today, there's dozens of materials, all different types of hardnesses to suit all types of environments, both temperature and compatibility-wise. In the 50s, we had the advent of what is really kind of the modern sealing technology, and that was understanding that as seal pressures were increasing after the war, pressures were going from 1500 psi hydraulics to 2500 psi hydraulics. And the problem with that is that it started to introduce new problems to those rubber O-rings. We were seeing the rubber turning, rotating in the groove, producing spiral failure and hysteresis and some of the things that can occur. O-rings as seals really are best suited for static conditions. That's the bottom line. And when you put an O-ring in a dynamic condition, it opens up a lot of potential for failure. Those being, again, hysteresis, thermal fatigue, spiral failure. Those are fairly common occurrences. And rubber seals are also prone to compression set over time with a combination of pressure and heat. So in the 50s, the early 50s, when DuPont introduced this new whiz-bang material called Teflon, some of the early seal designers started to use Teflon for backup rings or anti-extrusion rings. A lot of the mill standard backup rings that were invented back in the early 50s still utilize virgin Teflon in forms such as single turn scarf cut backups and double turn scarf cuts. There's solid backups. There's all kinds of different configurations, but they all still use virgin PTFE even to this day. As pressures continue to go up, there are some applications where an O-ring and a backup ring or two backup rings are perfectly adequate for design. But it was out of that advent of PTFE as an anti-extrusion ring that a whole new family of seal technology came into being called slipper seals. Now, slipper seals are really an interesting concept in that you're basically taking a material, a PTFE, which is low friction, generally a good wearing material, very durable material, and you're placing a thin section of that material in between the dynamic surface, whether that's the bore or the rod, and keeping the O-ring static, which, as I mentioned earlier, is really the condition that we want a rubber O-ring to be in, is in a static condition. So slipper seals really were being pushed as temperatures and pressures went up higher and higher. Stiction was increasing, so elastomers by themselves were no longer adequate. That's when the PTFE slipper seals really came into being. Now, this chart here that you're looking at is seal types as we know them today. Not very sophisticated. But you can see on the left side of the chart there's two columns, and these are considered to be classic compression type seals. These are seals that require a certain amount of either compression from a mechanical force, or they need a preload or an interference at their static condition in order to perform. O-rings typically will have a interference built in to the design of the gland of 12 to 16% squeeze. So, you know, that by itself tells you that you've got a certain amount of stiction that you're going to have to overcome with that really tacky, sticky material. And so it makes sense to introduce something in between that sticky, tacky material that is not so sticky and tacky. And that's where the cap seals or slipper seals came into being. But if you look at those two columns, it's really a combination of elastomers and other plastics, in some cases even metals, to produce a classic compression or interference fit design. In the middle there, you'll see what's classified as an intermediate design. This is in between a compression and a true lip seal, which is a pressure-sensitive seal. The intermittent designs are things like chevron packings, where you have less initial interference, but the introduction of pressure and sometimes a compaction ring or a packing ring will increase the amount of preload on that chevron packing. And same with the polypack style urethane seals, where you've got either O-rings or quad rings or a diamond ring. There's all kinds of different expanders that are used. But that elastomer is really in there to maintain a preload on the seal lips of the urethane. If you take those out, or over time and heat and pressure they take a set, you basically have taken away the preload mechanism for that urethane seal. So if you look at the true lip seal designs, which also include other types of chevron packings like PTFE chevron rings, a asymmetrical or symmetrical urethane seal that is machined or molded in a condition to where the basic design allows you to operate without an O-ring or an expanding ring. Those are true pressure-sensitive lip seals. And at the bottom you see there a PTFE spring energized seal, which we will be talking about. Now the key differences here by the designs are really generation of friction. The ones on the left tend to work better at low pressures. The ones on the right work better at high pressures. But it's friction, wear, heat generation. All these things come into play based on the geometry of the seal. Now, taking a look at compression type seals, O-rings, T-seals, the slipper seals that we're talking about, the PTFE, those all use elastomer expanders. Braided packings are also compression seals. Quad rings are compression type seals. These types of seals have excellent low pressure sealing capability. That's really, again, what elastomer seals are best at. However, the friction on the rubber on O-rings and T-seals and quad rings is much, much higher, and that produces more heat, and ultimately heat produces wear and failure. The use of these Teflon slipper rings between the elastomer expander and the dynamic surface obviously reduces the wear, reduces the heat and the friction without giving up that low pressure sealability. So it's a nice combination of sealability, wear performance, keeping the heat generation down by keeping the friction down. The intermediate designs, as I mentioned, are the urethane seals that use elastomer expanders. These are fairly traditional designs along with the chevron packings. These tend to have lower interferences to start with, depending more on system pressure to push down and expand the seal lips. The downside on this is the expander material does take a set over time and loses its ability to maintain the proper forces. So the urethane that is used is extremely durable. It's a little temperature sensitive. in that operating temperatures of urethanes are generally in the low to sometimes mid 200 Fahrenheit. A little bit higher friction, but they're very good in terms of their abrasion resistance and pretty good with their wear properties. And then finally, the chevron sets, they're depending on both compaction and pressure to be effective. The multiple sealing lips is always a good concept in that you're introducing a bit of a labyrinth design. The trick is to be sure that the introduction of all of those seal contact points is not producing too much footprint to where you generate a huge amount of heat. And with that much mass, it's very difficult to get rid of that heat. And as I said before, heat kills both polymers and elastomers very quickly. Now, as the hydraulic and pneumatic pressures are going higher, we've got these stiction issues. And since PTFE by itself does not have very good wear properties, we have to use additives. And so the advent of filled Teflons for seal applications came along very quickly when they found that virgin PTFE really does not wear very well. In fact, if you were to look at a tribology chart, virgin PTFE is off the chart within the first hour or so. It's literally a straight line right up. It wears that quickly. So what we're trying to do here is find the right polymer blend using the PTFE and using the right elastomer expander or spring and solving sealing problems by introducing slipper seals. Now, seal design, we really want to look at two unique facets. First is geometry, and second is material. The geometry has a lot to do with leakage control because of unit loading. If you look at some of the traditional PTFE seal designs, you'll see that they're generally designed to put the highest amount of force on the lowest amount of surface contact area. This is because we want to get the best sealability with the smallest amount of footprint area, again, to keep down heat, because heat generates wear, and that's the one thing we want to avoid. So the leakage is controlled by unit loading. The wear life, conversely, is also controlled by unit loading because of that very factor of heat generation. And the service type, what's the media? Is it hydraulic fluid? Is it water? Is it gas? Is it oil? Is it inert gases like oxygen or nitrogen? Those will have a critical factor when it comes to the geometry design. The application, static or dynamic. You can get away with a lot of things statically without using filled materials. Virgin Teflon does very well in static conditions, but it depends on the pressures and what else is going on in the environment. What's the type of seal? Is it a rod seal? Is it a piston seal? Is it a static face seal? And then finally, what are the hardware conditions? Installation situation. Some seal geometries can't be used on some very small diameters, especially on small rod seals, for instance. If you have a very intricate geometry, when you go to try and fold that seal to pop it into place in a closed groove, you could deform it beyond its usability. So we have to be a little careful about the geometry and how it's going to be installed. Now, in terms of material, especially with PTFE materials, since all PTFE is porous, we need to be aware of what fillers we're using and what technology we're using to make the material. We want to try and get the least amount of porosity, obviously, because if you've got situations with inert gases, for instance, you could be introducing flow paths right through the PTFE seal. So leakage is a very predominantly controlled by the material. Life as well. Different fillers produce different wear lives. So we look at the compatibility of the hardware, the media, the temperatures to be sure that we're getting the right fillers matched up with the PTFE. Again, looking at the service, what's the media, gas, oil, water, what is it? Temperature and chemical considerations. These are both critical. not so much in terms of the PTFE seal, but in terms of the expander material. If we have situations where we're introducing certain chemicals or certain high temperature or very low temperatures where elastomers are not going to work, that's where we're going to point you in the direction of a spring energized seal, which we'll talk about in a minute. And then finally, extrusion resistance. One of the advantages of a slipper seal is that you can actually increase your E-gap in your design because these materials are so extrusion resistant compared to an O-ring. So we'll look at those materials depending on what you're working with from your design standpoint, what kind of pressures are involved. I've seen applications where you can get pressure spikes in 3,500 psi hydraulics that could drive the pressures up to 8,000-10,000 psi in a momentary condition. So you need to be sure that that slipper seal material is going to be able to withstand that spike. So the number one rule I would mention to you here, seal geometry should never be used to compensate for an inadequate material, nor should a material be used with improper geometry. Basically what I'm saying there is that don't use the geometry to compensate for a bad material, and vice versa, don't use a good material to compensate for a bad geometric design. You really need to balance the geometry and the material to be sure that you're getting adequate sealability, low footprint areas is the lowest you can get away with. That's going to control your friction, that's going to control your heat generation, and ultimately your wear life. Now looking specifically at the geometry, the shape of the seal influences really all the areas of performance. That footprint or contact area not only establishes the leakage control, but it also establishes how much heat generation you're going to generate from friction and ultimately how long that material is going to last. The shape of the seal relative to the hardware, as I mentioned before, that is something that we have to work with you as the customer to be sure that if you're using a closed gland, that the geometry will be installable without damaging the seal beyond use. If you're using an open gland, obviously there's a lot of advantages to doing that, but it's generally a little more costly as well. And then service conditions are going to dictate ultimately what the geometry is too. Temperatures, speeds, pressures, all of these come into play. Now looking at some of the advantages and disadvantages of the materials. Elastomers, as I've mentioned before, really well suited for low pressure static seals. But when they're introduced to dynamics or to chemicals or to thermal conditions, you can get fatiguing, you can get compression set, spiral failure, extrusion failures. All of these things are potentially a disadvantage for elastomers. The advantages obviously are very good low pressure sealability, but again, best suited for static conditions. Urethanes, very tough, good cut resistance, good extrusion resistance. Urethane seals in many cases can go up as high as 10,000 psi. The temperature range and chemical compatibility is a little bit limited. Urethanes don't do well in certain chemicals at all, and the temperatures are typically going to be in the low to mid 200s maximum. And again, a lot has to do with the use of an expander. What is the expander material, and how does that match up with the temperature environment? Multi-part seals, these are like T-seals or the Skager or halite type, Prodifa type seals, where you've got an elastomer, you've got a couple of polymer influences there. You might have 3, 4, even 5 different components in one seal set. And so the downside of that is simply that you've got a lot of parts to handle, and you generally have a much larger gland that you have to work with. On the upside, these types of seals have very good extrusion resistance at the higher pressures. You've got a limited amount of elastomer contacts. You've got good low pressure controls, but again, you've got a lot of different parts that you have to be concerned about, and everything has to be there when you open up the bag. And so it's a bit of a stretch to try and make those work consistently. Again, the PTFE slipper seals, as we have mentioned, we've got literally hundreds of materials to enhance wear, reduce friction, improve extrusion resistance. We can seal over a very broad pressure range. The temperature is going to be dependent on the elastomer, but if we use Viton elastomers or fluorosilicone elastomers, you can get up into the 400 plus degree range. These types of seals do tend to be a little more expensive because of the PTFE component. So you need to be aware of that up front. These can be used as piston or rod seals, face seals, in all different types of media. Hydraulic, pneumatic, inert gases, some water seals. And then finally, spring energized PTFE seals. This is really kind of where we are specializing these days. It's a very high-end product for very difficult applications. Spring energized PTFE seals, where they really come into play, is if elastomer type slipper seals don't meet the chemical compatibility requirements or the temperature requirements, or you're concerned about compression set. In this case, we're using a spring energized seal where we've got a number of different spring designs, and those springs are made out of a number of different materials to be compatible with both temperature and chemical environments. Some of the design questions that we ask as we start talking about seal design. What's the pressure? And again, as with bearing designs, we don't want to just know what the normal operating pressure is, but what's the potential for pressure spikes, especially in hydraulics or gas conditions. You could get some serious pressure spikes, even dieseling effects. So we need to know what the potential is for that. What's the temperature range? The minimum, the maximum, and normal operating. What are your leakage requirements? I don't know that yet there's been a seal design that is absolutely dead nuts going to stop all leaks, but I know of PTFE seal design combinations that can seriously reduce to like 1 drop per thousands of strokes. So, what really is your leakage requirement? What's your hardware design? Open or closed groove? How far down is the groove? What kind of bearing support do you have for the seals? One thing about seals is you don't want to design seals to also operate as the bearing. That's a big no-no, and it will introduce failure to your seal very, very quickly if you try and do that. What are the speeds and the cycles? How many feet per minute? What's the cycle rate? How many strokes per minute are you running? What's the length of the stroke? Is it lubricated or is it dry? We have a lot of dry pneumatic applications where spring energized PTFE is very, very good in those environments. But is the lubrication, is it Skydroll, is it mill oil, just exactly what it is. And then finally, as with our bearing design program, we also like to know what your cost concerns are. Obviously, if you're looking to replace a rubber O-ring that costs you 20 cents and you want to try and solve your problem for 25 cents using a Teflon seal, I can pretty much tell you up front that that's not going to happen. So, tell us up front exactly what your cost considerations are, because it may be that PTFE seals are not the right direction for you. So, when urethane seals won't work, when O-rings won't work, when chevron packings won't work, and then when slipper seals don't work, that takes us now into really the top dog, if you will, in the seal world, and that is spring energized PTFE seals. When temperatures or pressures or chemical environments are above and beyond what any of those other seal materials or geometries can accomplish, that's when spring energized PTFE comes into play. These types of seals can operate from minus 400 to plus 550, even up to plus 600 with some materials. We can operate in deep vacuum up to 60,000 psi. In some applications, quite honestly, we'll use a spring energized seal and the spring will be an elastomer. There are some applications where that's important, like in certain compressor conditions, you can't have any dead space at the top of the piston. Then you need to have something other than a spring in there. So sometimes we'll use an elastomer or we'll combine an elastomer with a helical spring, something like that, to take up that dead space. With slipper seals, the geometry and material selection are very key to successful use. The same holds true for spring energized seals. We have hundreds of PTFE compounds to meet the pressures, the temperatures, the wear requirements, the flexibility requirements, and then ultimately what's the leakage control issue. We can introduce different lip designs. There's a number of different lip styles that we can bring into play into the jacket to meet both pressure and frictional needs. Unit loading is going to be controlled somewhat through the geometry and also through the spring shape and the load of that spring. We have different gauges of spring, so there's different forces being generated. The shape of the spring, the location of the spring compared to the seal footprint area, all of this comes into play into designing a spring energized seal. We have a lot of different spring designs and materials. We can make springs out of stainless, a couple different grades of stainless, Hastelloy, Inconel, nickel alloy materials. We have slant coils, we have ribbon springs, we have cantilevered beam or finger springs, rosette springs, helical coil, and all different gauges and loads. So a lot of variety can be introduced in both the jacket design, the jacket material, and the spring design and the spring material. All of that comes into play as we look at spring energized design. This is just a view of some of the different designs. We even have a picture there of some can seals utilizing both helical and V-spring or cantilevered beam springs. Cantilevered beam springs with RTV fillers for FDA applications or sanitation applications. Multi-lip springs, nested springs. You can see just a big variety of both the spring and jacket designs here. So the four primary lip seal designs, and there's variations on these themes, but chamfered lips, which we'd be using primarily in reciprocating bidirectional sealing. If you've got an application where you want to utilize a spring energized PTFE as a scraper, we can also design a high point scraper seal. Multi-lip seals, where we're in essence generating a labyrinth effect, and what really is key here is being sure that we generate the right amount of spring force on that very small footprint area. And then finally a bulb lip, which is kind of a universal design where we're using different types of helical springs and matching those helical springs up, and we can use cantilevered beam too, but matching those up to a much broader footprint area and spreading out the forces, if you will. So PTFE seals, they really come into play where there's a broad design need. Most of the time when we get involved in spring energized seal design or even slipper seal design, it's where everything else has failed. Rubber and urethane just don't seem to work. Then we move up to PTFE and one of these different styles of seal geometries. With PTFE, because they are machined, not molded, we have a lot of flexibility. We can design to oddball hardware conditions. We can enhance traditional slipper rings or spring seals to meet your specific needs. And then the advantage that we have at TriStar obviously is a very diverse selection of materials, and combined with the different geometries, we can offer a very, very good cross-section of design possibilities for you. So that's a quick look at PTFE seal design. I'm not going to stand here and try and convince you that it's rocket science. It really isn't, but there is some tricks to the trade. We're very fortunate to have some engineering people on staff that have a very long history in seal design, and so we feel very comfortable that we can look at your seal applications and maybe come up with some better designs, some better materials for you. So again, if you have some questions or have an application, you can go to the Ask the Expert site and fill out that site, or you can go directly to our worksheets and fill those out to us, or call us directly at the engineering department at 800 TriStar. We're happy to help. We're here to help, and hopefully that this bit of information has been interesting to you, and that next time you have a seal application or a real problem with your current design, think about TriStar. We're here, we're capable, and look forward to being of assistance to you. Thanks for joining us at Tech Talk. We look forward to seeing you again.